Have you ever looked at a map of the world? It's huge. It shows all the countries and oceans. Well, chemists have a map too. It's called the periodic table of the elements. It's a chart of every single kind of atom in the universe. It's an amazing tool. But even on this super important chart, scientists have a little disagreement. It's about one tiny spot on the map. It is in a column called Group 3. Two different elements are fighting for that spot. It's lanthanum versus lutetium. This debate might sound small, but it's a fun and important puzzle. It makes us think about what it means to be a family of elements. How do we decide who belongs where? The answer is all about patterns. Scientists call it the Le-Ac versus Lu-Ac debate. Let's solve this chemistry mystery together. Let's go. Getting the pattern just right matters. Okay, let's zoom in on our map. Let's find Group 3. The periodic table has rows and columns. The columns are called groups. Think of them like families. All the elements in one group have things in common. They act alike in certain ways. They have similar chemical personalities. Group 3 sits at the beginning of the transition metals. These are metals we know and love: iron, copper, and gold. Group 3 elements are metals. They're shiny, can be stretched into wires, and conduct heat and electricity. Think of a metal pan. Heat spreads. Group 3 elements are also pretty reactive. They love to form compounds by giving away electrons. Group 3 acts like a bridge to the two rows below called the F block. The top row is the lanthanides. The bottom row is the actinides. Group 3 is the gateway, so its membership is important. Everyone agrees on the first two members. The third and fourth are debated. It's like two cousins arguing about who stands next to Grandpa. Let's meet the family and the cousins causing the fuss. Alright, let's meet the family. Every scientist agrees on the first two. First up is scandium, symbol Sk, element 21. Below scandium is yttrium, symbol Y, element 39. They're locked in. Now who belongs right below yttrium? Two main candidates, lanthanum and lutetium. Lanthanum La, element 57, a soft, silvery white metal. Lutetium Lu, element 71, also silvery, but much heavier and denser. There's one more spot below that in the next row. Actinium Ac, element 89, usually goes there. One view says Sky La Ac, the other says Cy Lu Lr. Most agree Ac starts the actinides, so it's La versus Lu. Team 1, Sky La, then the lanthanides begin at cerium. Team 2, Cy Lu, with the lanthanides starting at lanthanum. Small chart change, big consequences for patterns. Let's dig in. This all comes down to electrons. Ready? To understand this debate, we need to talk about electrons. Imagine an atom like a tiny solar system, nucleus in the center, electrons orbiting. Electrons stay in specific energy levels called shells. Think floors and rooms. Floors are shells, rooms are orbitals. Orbitals come in S, P, D, and F shapes. The table maps how electrons fill these rooms. Filling order gives each element its personality. Lanthanum, La 57 electrons, with 5d and 6s occupied, and the f orbitals empty. Lutetium Lu, 71 electrons, 5d and 6s occupied, and a completely full f shell of 14 electrons. So what defines group 3? The single d electron at the edge, or what's happening in the f orbitals? One team favors elements about to start a filling Le. The other favors elements that finished a filling Lu. Beginnings versus endings. Now the case for lanthanum and actinium. Let's hear it. This is the more traditional view you'll see in older textbooks. Group 3 as scandium, yttrium, lanthanum, and actinium. Lanthanum is 57. The next element, cerium, 58, really digs in and starts filling f orbitals. Start the lanthanides at cerium and end at lutetium. Exactly 14 elements. The f orbital holds 14 electrons, one element per electron. Clean and tidy. Lanthanum acts as the prototype leading into the lanthanides. Chemically, La flows into Ce and Pr. They all like the +3 ion and share similar properties. Think of La as team captain standing by the pitcher row, introducing the group. This view prioritizes a smooth lanthanide story and a neat 14-element block. That's the case for lanthanum and actinium. Now, what about lutetium? Let's switch perspectives. Welcome to Team Lutetium. They argue for Sc, Y, Lu, and then Lr, with Ac often shown for simplicity. Lutetium has a full F shell and 1d electron. Scandium has 1d electron. Yttrium has 1d electron. Lutetium matches that pattern. Define group 3 by the d electron edge. Now the group is consistent. This alignment smooths trends like atomic radii, ionization energy, and melting points. The F block becomes Le to Weib, 14 elements, while Lu graduates to group 3. In the lineup, the coach insists, pitchers only in the pitcher row. Lu moves with SC and Y. Many organizations, including IUPAC, lean this way for consistent rules. SCY and Lu line up cleanly. How do La and Lu compare physically and chemically? Size, weight, and reactions. Let's see. Onward. So, we've looked at the electron arguments. What about the elements themselves? On a scale or with a ruler? Lanthanum is relatively large for its neighborhood. Lutetium, despite more protons, is smaller due to lanthanide contraction. Lutetium is much denser. A same-size cube feels much heavier than lanthanum. Lu's density is closer to yttrium's than lanthanum's is. By size and density trends, Lu fits group 3 slightly better. Point for Team Lutetium. Does this debate change anything in the real world? Nope. Lanthanum is still lanthanum wherever you draw the line. These elements are super useful. A pinch of scandium makes aluminum strong and light. Bikes, bats, and even jet parts. Yttrium made red CRTs glow, builds lasers, and appears in superconductors with zero resistance. Yttrium also helps in some cancer therapies. Lanthanum oxide sharpens camera and telescope glass. Bends light without smearing colors. It's used in many hybrid batteries. Lutetium isotopes power PET scans that let doctors see inside the body. Lutetium can speed up reactions as a catalyst. They're part of the rare earths, not super rare, but tricky to separate. Understanding their chemistry helps us mine and use them better. Debate sharpens that understanding. Whoever wins, these elements already win in daily life. So, what's the big idea? We have a friendly scientific debate about one spot in group 3. Team Lanthanum keeps a neat 14 from cerium to lutetium and matches some chemical properties. Team Lutetium makes electron patterns consistent and fits physical trends like size and density. Who is right? Science isn't about final certainty. It's about the best model from the evidence. Right now the evidence is split, but the community is leaning one way. Many groups, including IUPAC, favor lutetium and lawrencium in group 3. Change is slow. Posters, textbooks, and websites take time to update. Both tables are useful day to day. The debate itself is valuable. It makes us examine our rules. The periodic table is a dynamic tool that evolves with our understanding. Next time, check if you see La or Lu, and remember the story behind that box. Science is a continuous journey of discovery. Consider this.